Okay, everybody. Good day, everyone. We started describing data with graphs. Describing data with graphs. Describing data with graphs. Okay. And in this class, we've looked at data can be qualitative and can be quantitative. And quantitative can be discrete and can be continuous. Okay. And now in terms of qualitative, we've used pie charts to describe qualitative. We've used a bar chart, and we've seen how those works. Okay. See data, qualitative, quantitative, discrete and continuous. Okay, so we've seen how to use to graph categorical data. You know, sometimes categorical data is another name and another word for qualitative data. Okay, so we've seen how to construct relative frequency. Now you have this a table, right? Suppose you have this table, and the number of times you have rating A is 35. Rating B occurs 260 times. Rating C occurs 93 times. Rating D occurs 12 times. So the total rating is 400. Okay. Now, if you want to construct pie chart with this, you need to have what is called relative frequency. Relative frequency. That is, you divide each of the frequency here by the total. 35 over 400, 260 over 400, 93 over 400, and 12 over 400. Okay, now for the pie chart, you have to multiply all these columns, each of them by 360 degrees. Okay, we've talked about that in class, and that is exactly what you have here. And the angles are represented here. And you can easily describe, anybody looking at this pie chart knows that, oh, B is the main guy. B is dominant, right? Dominant. All right. You can easily make decision from the figure. Quick, easier. It's a lot easier than using only tables. That is the benefit. And you can use a bar chart. See, bar chart has got some spaces in between the stripes here. Okay, that is bar chart. Okay. Now for A occurs how many times? 35 times. See, so this is about 35. B occurs, so it's also easier to see them, right? Actually, there is these are common and make more sense than most other graphs. Okay, so pie chart. If you don't know about any chart, at least pie chart, you should remember bar chart. This can easily be used for what? Qualitative, to describe qualitative data. Now we move to, you can have many examples. Look at this table. We talked about this table yesterday. You develop the tally for them. This frequency, relative frequency, this is the percentage. Okay, so each angle equals relative frequency times 360 degrees. Very simple, right? So that's the bar chart for the same figure here. That's the bar chart. Look at brown. Brown occurs how many times? 6 times. So that's highest, 6 times. That is for brown. And blue, color blue occurs 5 times. That is blue. Okay, different colors. Sorry, those are the daycare kids making noise there. Colin is making noise. Forgive me, my wife runs the daycare in our house. So that's why. So you can go through this and practice more examples on what? Pie chart, bar chart. So you count how many of them, you develop the tally just similar to just follow this table. Just follow this table, okay? Right. Now, that is for qualitative. Now, let's move to quantitative data. Now, quantitative measures variables, measure an amount of quantity on each experimental unit. Quantitative variables measure an amount of quality on each experimental unit. So if the variable can only take a finite or countable number of values, it is called a discrete, like I told you in class. A variable that can take on infinite number of values correspond to a point on a line is called, or a line interval is called continuous. Remember in class yesterday, I told you if you are in a real line, right? If X is a member of this interval, that is X is a number, is any real number that can be found on this interval, then the number of X here is uncountable because it's not 2. You can have 1.01, you can have 1.001, you can have 1.00, you can have uncountable numbers, real numbers in that interval. But if I tell you X is a member of this interval and X is a positive integer, then the number X can only have 2 values. X can only be what? 1 or 2. Because I am restricting my X to be what? Just integer without decimal point. All right. So now you can also use pie charts and bar charts to describe quantitative data. Okay, you can also do the same thing. You can do the same thing. So I'm going to skip that aspect because we've already done it. So this is a what? This is a quantitative. How do we know it's quantitative? Because of the decimal point. Now, I told you yesterday, if you have numbers like 1.1, 1.2, 1.3, 1.4, and 1.5, evenly spaced, this may be discrete. This may be discrete. Okay. Now, let's have that example once again. You know, if you have multiple examples, it will always help. They will always help you. Now, the amount of money expended in fiscal year 2016 by the U.S. Department of Defense in various categories is shown in table 1.5. Use both pie chart and bar chart to describe the data. Very easy, right? So this is the total, all right? And you remember you have to add up everything and do your what? Relative frequency. You divide each of them by the total. The total is 5, total of this column. If you add up this column, the total is 580.3. So you divide each of them by the total. You know, like that. 244.4 divided by what? 580.3. And you will get, and then after doing that, you multiply. Suppose this column is called B. Then you multiply each of the column B here by 360 degrees, and you get an angle there. And that is exactly what you have right here. And those angles can be visualized in terms of pie chart or bar chart. Now, the bar chart, it's a lot easy, right? Now, military personnel is in million. The expense is about 138.6. So now you have to tell us in your graph scale, you have to tell us, hey, my graph here is in millions, because we cannot write, you cannot write 250 million right on this graph. It's going to be very messy. So, and you have to tell us, hey, the amount on this vertical axis is in millions. Okay, so military personnel has got 138.6 million, which is around here. Okay, and then you space them around 244, category B. You can space them evenly. You can space them evenly, maybe by 2 units. So it doesn't matter. Okay, so you can use pie charts and bar chart, or for both qualitative and quantitative. Now, the next chart here is a line chart. Line chart is the most primitive one and very popular, which can be of this form, like you draw a line, right? Y-axis, x-axis, bam. So it's also very useful. It's also very useful. So when a quantitative variable is recorded over time at equally spaced intervals, such as daily, weekly, monthly, quarterly, yearly, the data set forms a time series. Time series data mostly can be easily, effectively represented on a line chart. So yes, so your data will be here and time scale will be here. Data vertical, time measure horizontal. Okay, so when you have time series data, line chart is very, very useful. Okay, now I won't read all this. I'll just go straight. So you have a year, population growth projections, okay, is shown in this table from 2020 up to 2060. They want to project the population growth. Okay, so this is what quantitative. So the quantitative variable 85 and over is measured over 4 times interval. Okay, of people who are 85 years and below and above, over 4 times interval. So 1 interval, 2 interval, 3, 4. So between this and this is the first interval. Between 91 and 14.6, that is the second interval. Between 14.6 and 19, that is the third interval. And between 19.0 and 19.7 is the fourth interval. Okay, so you need 5 data to make 4 intervals. So you need n data to make n-1 intervals. Okay, so that is the graph here. Look at that graph. Now, look at that. You have 6.7, 9.1, 14.6, 19.0, 19.7. They are here. Our data is always on the vertical axis. And the year 2020, 2030, 2040, 2050, 2060, the year are horizontal. The time measure is on horizontal axis, while the actual data is on vertical axis. Okay, so this graph is actually the same, except that this is being converted, I think, into is that percentage? Let's see. Both are very similar. I think what is going on here, it's this 7.5. This data, they are converted to something else. I want to assume, let me check. Okay, now the intervals are marked on horizontal axis and the projections on the vertical axis. That's our data. Data points are then connected to form the line chart. So notice the differences in the vertical scales of the two graphs. The shrinking scales on the vertical axis causes large changes to appear small and vice versa. To avoid misleading conclusion, look carefully at the scales of the vertical and horizontal axis. However, from both graphs, you get a clear picture of the steadily increasing number of those who are 85 and older over the next 40 years. I think this were just converted to this scale. And I want to believe, yeah, okay. I know what that means. It's not actually conversion. Now, this ranges from 5 to 20 points according to this. Yeah, I got it now. Sorry. Look at it. Okay. But if you want to make it neater, instead of going from the minimum to smallest, you can just go from 0 to 100 and then represent all your data right here. Now, remember, the maximum is just 19.7 here. So it's going to be between 0 and 20. That is why this came down. Okay, it's not actually any conversion. And you can also use what is called a dot plot. A dot plot. So many set of quantitative data cannot easily be separated into categories or interval of time. You need a different way to grab this type of data. And one example is dot plots. Why do we need dot plots? For small measurements, okay, that are not easily represented as well, and that are not easily separated into categories or interval. So when you cannot easily separate your data into categories or interval, and they are very small, use dot plots. Use what? Dot plot. Now look at dot plot. You have numbers 2, 6, 9, 3, 7, 6. Okay, now you will now, what you can do here is you can spread out numbers from the minimum from 2 to 9, because we know that all these numbers are contained between 2 and 9. So 2, 3, 4, 5, 6, 7, 8, 9. And then 2 occurs one time, dot. 3 occurs one time, dot. There is no 4, so you skip that. There is no 5, you skip that. Then 6 occurs 2 times, dot, dot. 7 occurs one time. So you can easily see that, that's called a dot plot. It's super easy to use, okay? And that is what is called stem and leaf plot. Stem and leaf plot. So another simple way to display distribution of quantitative data is stem and leaf plot, okay? This plot uses the actual numerical values of each data point. How is it done? You divide the measurement into 2 parts called stem and leaf. List the stems in the column with the vertical line to their right. For each measurement, record the leaf portion in the same row as its corresponding stem. Order the leaves from the lowest to the highest in each stem. Provide a key to your stem and leaf coding so that the reader can recreate actual measurement if necessary. Okay, now look at what we have here. Bam. Remember, you can still use pie chart for this. You can still use bar chart for it. And you can also use, you can even see, but if you want to use dot plot is for small. So you cannot use dot plot here. It doesn't make sense. Another thing to use is what is called stem and leaf plot, which has been described here. So look at it. Now you have to look for the minimum here. Minimum is 40. The maximum is 90. You have all of them, so 4 to 9. So you have the stem has to be what? 4 to 9. Does it make sense? See, the minimum is 40. Minimum equals 40. Maximum equals 90. So you have to use your stem. Your stem, because you have stem and leaf in this side. Leaves here, stems here. So your stem, we have to range from 4 to 9. Okay, so 4 to 9. Now, do we have 40? Yes, one time. So 40. Now, do we have 50? None. No 50. Now we have 60. We have 65. We have 60, 68. We have, you have 60 something. So you have 65, 6 and 5, 65, 6 and 8, 68, 6 and 0, 60, 6. Now you have them the way, the way they appears. If you list all the 60 something here, okay, if you list all the 60 something here, we have 65, 68, 60. The next one is 68 again, 65 again, and 65. Now, if you pick, the first one is the stem. The first number is the what? Stem. First digit is the stem. If you pick 6 out, that's the stem. That is 5. That's 5. That is 8. 0. Another 8. Another 5. Another 5. That is exactly what is going on here. That's what you do. And then you can, if you like, you can arrange it in order. It doesn't matter. So this is just sorted. Arrange it from smallest to largest, see from 0 to 8. Or you can leave it this way. Okay. Now, leaf unit equals 1. The leaf unit is 1, just 1 unit, okay? Unit 1. So you can have 7. Let's see another one. Let's see another one. This is another option. Now, I'm not going to read this table for you. I'm going to look at this table. Birth weight of 30 full-term newborn babies. Okay, so now you look for the smallest. That's the first thing you look. You can write the program to do that. Look for the smallest. 5 point something, 5.6, and the largest is 9.4. So you have to all your stem. Your stem has to be from 5 to what? To 9. Okay, 5 to 9. So you can do that now, and you don't have to list them 5, 6. So you have that. So you have, now be careful of one thing here. Be careful of one thing here. This is this has got decimal point. This has got decimal points. So you have 5.8, 5.8 and 5.6, 5.6, 5.8. Where is that? They're just here. Look at it. And you have 6.1. And where is that? 6.2, 6.1. They are here. Yeah, or you may choose to put all this one right here. Okay. But for this type of data, it's more meaningful if you separate them. So it is also valid. You can have a number repeated twice in the stem column. You can have 6, 6, or you can have it only one time, and then you have to merge up this and this. Okay, so stem plot. So what is stem plot again? You have stem portion versus leaf portion. And when you do it, you have to describe the units. So the unit here is 0.1 because of decimal points. So that somebody reading this will not tell you, hey, your first data is 58. No way. It's 5.8. So the leaf unit is what? 0.1. Okay. All right. So what have I said briefly there? I'm just saying that instead of spreading your stem portion this way, You may decide and write all the 5. You may decide to write it this way because I know I've got multiple 60 something. So I can have 5, 6, 6, 7, 7, 8, 8, 9. Make it longer. And then I've got 5.8. So that is that. I've got 5.6. That is. Now you have to put space between them. And I've got 6.1. So 1, then space. I've got 6.2 here. So I've got 6. Now 6.8, 6.8, 6.8. I've got 6.7. Then you have to tell me the leaf unit is actually read as 0.1 because somebody's looking at this. If you don't put the description here, somebody can interpret this as what? 58, and that is not right. So it is 5.8. Okay. So, and let's talk about, you can easily interpret graphs with your critical eye. I'm telling you, okay, you can have what is called outliers. Outliers is data that is exceptional. If everybody is scoring 45, 45, 48, 49, and there's a very smart guy that got 99. So you regard this 99 as what? An outlier. So when you describe data, a distribution, now distribution means just set of numbers. Like this is a distribution now. This is a distribution. This is a distribution. Numbers are distributed. Numbers are distributed. So a distribution may be symmetric if the left and right sides of the distribution when divided is at the middle. Now let me tell you the meaning of symmetric distribution. Right? This is a dividing line, and I've got this. See how this line divides the parabola into 2 equal parts? So this is a symmetric distribution. Does it make sense? I believe so. Okay, and you can, I think I've said it in the class, a distribution can be skewed to the right. This is a right skewness. And it can be skewed to the left. See? Okay, and you have a unimodal distribution as just 1 peak. You have a bimodal, 2 peaks. You can also have multimodal, more than 2 peaks. Okay, what does that mean? That means you can have a distribution. This is one measure, this is one type. This is type A, type B. Now, if your type B and type C has got the same frequency, then this is type D. Maybe type D is 3. Now you can see that B frequency for B and C are both 8. So the mode of the distribution is what? B and C. That is bimodal. Okay, I think you understand what that means. They are very easy. Okay, and and look at this shape. Obviously, this is symmetric. Okay, this is what? Left skewed. I think. See, most of the data to the left. See, a lot of frequency. Most of the frequency falls to the left side. This is a uniform. This is a uniform one. It's a uniform one. And this is what? Right skewed. Right skewed. See what we're doing? So you can have a uniform, you can have a, okay, see, this distribution that are skewed to the right contains a few unusually large measurements. Okay. So once again, let's look at it. Let's look at those things again. This is a symmetric, almost the same shape to the right and to the left. This is a uniform. It's uniform, all the same thing. This is what left skewed. Most of them fall to the left side, and this is a right skewed, okay? All right, so this is a dot plot, which I'm not going to do again. I think that should be it for now. And I think you also have what is called relative frequency histograms. Relative frequency histogram, that should be the last thing to be. Relative frequency histograms. Now, that is another chart that you can use to describe quantitative data. Okay. Now, in the relative frequency, you have these measurements. Now, to represent, look at it, a relative frequency histogram resembles a bar chart, but it is used to graph quantitative rather than qualitative. Okay? So first, you divide the interval from the smallest to the largest into sub-intervals or classes of equal length. So a class is a sub-interval created when you divide up the interval from the smallest to the largest. Class boundaries are the numbers that create the upper and the lower limit of the class. Class width is the difference between the upper and the lower class boundary. Class frequency is the number of measurements falling into that particular class. Relative frequency histogram for a quantitative data is a bar graph in which height of the bar shows how often, okay, how often measured as a proportion of the relative frequency measurement fall into each sub-interval or class. So the classes or sub-intervals are plotted along the horizontal axis. Now let's have an example here. Now, this is a very good example. Okay, now choosing the number of classes. So here, from the table 1.9, the largest is 9.4. The smallest is what? 5.6. So you subtract the smallest from largest to get what? 3.8. Okay, 3.8. So that is a kind of so that is where how you start from. And choosing the number of classes, you can have sample size to be 25. You can have sample size to be 50 for class 7, sample size to be 100 for class 8, sample size to be 200 for class 9, 500 for class 10. And now let's see how it works. So you have 8 classes. 8 what? 8 classes. 8 classes. Now, how is it done? For the birth weight, we decided to use 8 classes of equal length. You may use more than 8. So the number of classes you use is up to you. But normally, your data will determine that most of the time. So you have class 1 to 8. Anybody from 5.6 to 6.1, you have 2 of them. From 6.1 to 6.6, you have 2 of them. Okay. From 6.6 to 7.1, you have 4 of them. Okay. So this is the class. You know, we made up this class based on the interval here. And the tally is normal, of course, easy. This is the class frequency. Now, you remember relative frequency, you have to add up all this to get 30, and then you do your relative frequency here. And then, so when you plot it, your relative frequency will be on the vertical axis, and your graphs will be here. See, there is no space. There is no space here. I think I will have to stop here because of I don't want it to be too long. And I hope this has been very informative for everybody. I will see you in class.